Okay, Assalamualaikum and very good morning. Today we will continue our topic about the introduction of second law of thermodynamics. Okay, actually it has 4 things. Okay, as you know, it has 4 things. Okay, right here. Okay, can you see that?
Yes.
Okay, actually the quality of energy, it works when the high temperature is produced, then more work to do. Okay, then about the direction of process. Okay, actually for example hot water, you bring it hot coffee lah. Hot coffee, you bring it into this air conditioner room, it can become more hotter. It will produce a thermal equilibrium, so the hot coffee just now will become warm. Okay, it can be more hotter when it is placed in the cold room. Okay, understand?
Yes.
Okay, next we proceed about the heat energy. Heat engine. Heat engine actually it convert. Okay, heat engine actually it convert heat energy in useful work. It requires the heat addition and rejection, such as the work can converted into energy, and energy is converted into work. Okay, it has a formula for this heat engine, thermal efficiency. Network output is divided into total heat input. Okay, like this. Okay, this is the formula. We can derive it become okay. Sorry. Okay. This is the equation of this heat engine. Okay. Any question for this formula?
No.
Okay, do you understand?
Yes.
Okay. Now we proceed. I have one example. You can look at on your textbook, page 513. Okay, can you see the example?
What
Okay,
page?
example 513, page 243. Okay, it said a steam power plant produces 50 megawatts of net work while burning fuels to produce 150 megawatt of heat energy at a high temperature. Okay, the question asks us to determine the cycle thermal efficiency and the heat rejected by the cycle to the surrounding. Okay, we write the detail first. Okay, what they give, okay, here QH equal to 50, QL is given 150 megawatt. Okay, now using this equation, okay, we have to determine the thermal efficiency. Okay, now, okay, first step, we should divide, okay, QH divide by, okay, first about the cycle thermal efficiency. 150 over 50, QL is divided by QH. We get 0.333, or we can simplify it as 33.3%. Okay, next the question asks us to find the heat rejected by the cycle to the surrounding. Okay, we use this formula. Okay, I write here. QL is equal to QH minus the net out. 150 megawatts minus 50, you get 100 megawatts. Okay, this is the solution. Okay, you get it?
Yes.
Okay, that's all. Okay, now we move on about the refrigerator and heat pumps. Okay, it defined as the absorbed heat from lower temperature medium and reject it to the higher temperature ones. Okay, for example, the person who has the fever, okay, he or she has a high temperature, body temperature, like 40 degrees Celsius. So, actually the thermometer has a standard temperature around 27 degrees Celsius. So when the person who has the fever, we what we call, yeah, we sketch for you about the refrigerator diagram. Okay, this is the diagram of refrigerator and heat pumps. Okay, first this is the compressor. Around 45 degrees Celsius. Then it will move to this. This is for the step 1. Okay, this is compressor, 45 degrees Celsius. Okay, step 1 is for gas compression. Now it will flow move to the converter, not condenser, where the air, the temperature will decrease to 30 degrees Celsius. For this condenser, it actually for liquefaction and heat is lost to surrounding. Okay, now it will turn to the evaporator. Not evaporator. Okay, expansion valves actually. Okay, this is expansion valve. Then for this, it has for heat and cold reservation. This is the evaporator. Evaporator, the temperature will decrease. Okay, the air temperature will decrease. Then it rotate again. Okay, are you understand?
Yes.
Okay. Now about the coefficient of performance, it react with the refrigerator and heat pumps actually, COP. Okay, it is desired result over required input. Okay, for refrigerator, it has its own formula, COP. Okay, this formula actually apply for the first law of cyclic refrigerator, which the basic formula for this is equal to delta E is equal to QH minus QL. This is for refrigerator. Then for heat pumps, it also have its own formula. Okay, this is the formula. I write here. Okay. This is the formula of heat pump. When it is under same operating conditions, mean that COP HP is equal to the COPR. Okay, for refrigerator also, it will react by COP this heat pump and also the refrigerator. Okay, now move to the second thermodynamic law, which is Clausius and Kelvin plan. Okay, actually Clausius, it require heat pump or other device that we need energy input. But Kelvin plan, we need the energy flow rate temperature. That's the difference between them. Okay, dah about the reversible and irreversible process. Okay, actually process reversible is that process that can be reversed. For example, the oscillation of pendulum. Okay. Okay, this pendulum, it will move to move like this. So it move then reverse back again. Okay, this is reversible process. Okay, for irreversible process is process that are not reversible. There's two things for friction and also heat transfer. Okay, friction, it is cause of heat transfer to the surroundings. So it cannot use the lost energy. So that's why it can't be reversed. For heat transfer, it cannot reverse the process without the heat pump. If it has the heat pump, maybe the process will reverse. But then the heat transfer, we find it of the change of temperature, it does not heat pump. So the electricity required for heat pump will affect the environment. Okay, the Carnot cycle. Okay, we move on the Carnot cycle. First, okay, drawing first. Okay, you can copy this drawing if you want. about the Carnot cycle, the process where the Carnot is functioned. First, about the isothermal expansion, we will need the QH to process of hot reservoir. Then for adiabatic expansion, isothermal compression, where it will decrease the QH of a cold reservoir, and also adiabatic compression. Yes, this is about the Carnot cycle. Okay, Carnot cycle, one of the example is about the Carnot heat engine, where it have two formula about the irreversible and reversible process, and also of Carnot heat engine only. Okay, this is the formula of, I write it here. Okay, this is for the irreversible and reversible process of Carnot cycle. Okay, in Carnot cycle, for heat engine only, okay, this is the formula. Okay, we can apply it for this example. Okay, the heat pump is to be used to heat the Zidane house at Madrid during the winter. The house is to be maintained at 20 degrees Celsius at all time. The house is estimated to be losing heat at a rate of 135,000 kilojoules per hour when the outside temperature drops to -5 degrees Celsius. Okay, so determine the minimum power required to drive the heat pump unit for this outside temperature. Okay. Okay, wait. Okay, this is the Zidane's house. About it has 21 degrees Celsius for the room temperature of this time. Then the flow rate energy is about dimension 135,000 kilojoules per hour. Next, okay, it said the flow rate of L is -5. So, 5 degrees Celsius. Okay, using the first law, using the first thermodynamic, we use the COPH. The formula is about QH0 over QH0 minus QL. Okay, then is also equal to TH over TH minus TL. Okay, so 21 plus 273. The temperature should be in Kelvin. That's why we plus 273 and divide by 21 plus minus -5. This, okay, we get the answer, which is 113.1. This is for COPH. Okay. Okay, by using the basic definition of the COP, when the QH is equal to Q loss because the T house is maintained. Okay, the QH is equal to the Q loss because the temperature in the house is maintained, which is 21 degrees Celsius. Okay, I think that's all for class today. We meet again. See you. Thank you. Assalamualaikum.
Mike.